So hello everyone, today we are going to study class 9th math and the topic 1.2 rational numbers. We saw in the previous section that there may be numbers on the number line that are not rational. In this section we are going to investigate these numbers. So for all the numbers you have come across are of the form b by q, where p and q are integers and q is not equal to 0. So you may ask, are there numbers which are not of this form? There are indeed such numbers. Let us formally define these numbers. A number s is called irrational if it cannot be written in the form p by q, where p and q are integers and q is not equals to 0. You already know that there are infinitely many rationals. It turns out that there are infinitely many irrational numbers too. Some examples are under root 2, under root 3, under root 15, pi, 0.10110, 1110, 11110, and so on. Recall that when we use the symbol under root, we assume that it is the positive square root of the number. So under root 4 equal to 2, so both 2 and minus 2 are square roots of 4. Some of the irrational numbers listed above are familiar to you. For example, you have already come across many of the square root listed above and the number pi. The Pythagoreans proved that under root 2 is irrational. Later, in approximately 4 to 5 BC, the Theodorus of Cyrene showed that under root 3, under root 5, under root 6, under root 7, under root 10, and under root 11, under root 12, under root 13, under root 14, under root 15, and under root 17 are also irrationals. Proofs of irrationality of under root 2, under root 3, under root 5, etc. shall be discussed in class 10th. As to pi, it was known to various cultures for thousands of years. It was proved to be irrational by Lambert and Legendre only in late 1700. In the next section, we will discuss why 0.00 this number and pi are irrational. Let us return to the question raised at the end of the previous section. Remember the bag of rational numbers. If we now put all rational numbers into the bag, will there be any number left on the number line? The answer is no. It turns out that the collection of all rational number and irrational numbers together make up what we call the collection of real number, which is denoted by R. Therefore, a real number is either rational or irrational. So we can say that every real number is represented by a unique point on the number line. Also, every point on the number line represents a unique real number. This is why we call the number line a real number line. In the 1870s, two German mathematicians, Cantor and Dedekind, showed that corresponding to every real number, there is a point on the real number line, and corresponding to every point on the number line, there exists a unique real number. These are Dedekind and Z. Cantor respectively. Let us see how we can locate some of the irrational numbers on the number line. So here we are given example 3. Locate under root 2 on the number line. It is easy to see how the Greeks might have discovered under root 2. Consider a square OABC. This is a square OABC with each side 1 in unit length. This is 1, this is 1, this is 1. As you know, it is a property of a square that each side is equal. Then you can see by the Pythagoras theorem that OB equal under root 1 square plus 1 square equal under root 2. How? Let's see. Under root 1 square plus 1 square equal under root 2. 1 square is 1. 1 square is 1. So it comes under root 2. How do we represent under root 2 on the number line? This is easy. Transfer figure 1.6 onto the number line, making sure that the vertex O coincides with 0. Vertex O coincides with 0. We have just seen OB equal under root 2. Using a compass with center O and radius OB, draw an arc intersecting the number line at the point P. Then P corresponds to under root 2 on the number line. As the same method, you have to locate under root 3 on the number line. So try. Exercise 1.2. So on the next video, we are going to do exercise